we have talked about the Calc 3 is the easiest of the calculus classes because we already know two of the three things that we do. We know derivatives and we know integrals. We just need to learn how to apply those things to functions of more than one variable. We just need to add to the describe stuff part. What that means is that this describe stuff part is where we're going to be spending most of our time. We're going to learn how to describe stuff, and then we're going to start thinking about derivatives, and we're going to think about integrals and think about how those concepts apply to this new thing we learned about. The same transition that we had when we moved from arithmetic to algebra. Algebra is just arithmetic applied to polynomials, which are just numbers of base x instead of base 10. So let's think about what we need to remember about derivatives and integrals. When we think about derivatives, we usually have in this category, we think of the slope of the tangent line. So derivatives told us about the slope of the tangent line. We also talked about derivatives when we wanted to discuss the instantaneous rate of change. I want to modify that just a little bit by saying the direction that we're headed. Think of the derivative as telling us about the direction, because that's what the slope represents. The slope is just a direction. It's saying which way we are going. We really kind of restricted ourselves when we developed the slope, because we noticed, like I was there, we noticed that there's an x direction and a y direction, and we can describe a line with just one number called the slope. The slope is the ratio of how much the y changes to how much the x changes. So this was a great idea when there's only two variables. It's like, oh, let's describe this direction as a ratio. Then we all went around and high-fived each other. Heck yes. We can get two things for one thing. Slope is rise over run. How much y is changing divided by how much x is changing. And then someone was over on the other side of the table saying, well, what if there's more than three variables? So we threw that guy out the window and went back to high-fiving each other. That's okay. That's what Calc 3 is for. What if there are more than three? That guy survived the fall and he came back and he's Calc 3. So derivatives tell us about the slope of the tangent line. So if I got a function, how low can I go? I better scroll. One of the things I've noticed is that there's no spring training for teaching. Like this is the first time these particular pens actually been out in like 2.5 months. So we'll start by restricting ourselves by saying y is a function of x. Pretty hard restriction, but it's okay. We got to start somewhere. The derivative tells us the slope of a line tangent to the function at a point. So the derivative tells us the slope of the line tangent to the function at a given point. We interpret this as the instantaneous rate of change. It's the speedometer of the function. But it's telling us which direction the function is going. Because if we have a train moving along these tracks and at x equals c is where the train leaves the tracks, then it'll keep going in this straight line. So that's what I mean by the direction. If we want direction information, we're going to be wanting derivative information. If we want linear approximations to a function, we're going to want derivative information. How's everybody okay? You're like, oh, we don't know. You got mad at us earlier when you said we were okay. Now you can be okay because this is old stuff. You're like, well, yes, I remember this. Or at the very least, you're like, oh, yes, I'm going to pretend to remember this. Wait, is there going to be a quiz? No, not today. Then I remember this very clearly. That's how we're going to think about derivatives. We don't want this thinking to change. We don't want this process to change. We just want to upgrade what we're thinking about. Let's move over to integrals. So if derivatives are slope of the tangent line, integrals we like to think of as area under the curve. I'm going to add to this a little bit because we usually stop at area under the curve. We always try to say as little as possible while still saying everything. But I want to emphasize a point. Area under a curve and above an interval on the x-axis. We usually leave off that above an interval because we're working with functions of one variable. And so the only thing that the floor could possibly be is an interval. Start at A, end at B. If you have another interval, that's just a completely different room. So you write a whole separate integral for it. The only thing that the floor could be, since we have one-dimensional floors, is an interval from A to B. But what we're trying to do is find out how much space is under the graph of the function and above whatever we decide is the floor. Still restricting ourselves to functions. Pretty heavy restriction to say y has to be a function of x, or x has to be a function of y. Glare. These are the two big questions that we dealt with. I want to add to this integral what I thought when we thought the same way I want to add the derivative thing. If you are unfortunate enough to be in my class, you know what I'm about to say. I'm going to talk about integrals. And you know what I'm going to tell you about integrals. Integration is multiplication, but one of the factors is continuously variable. That's what's going on with integrals. I don't have enough space to write it here, so I'm going to write it down here. Integration is multiplication but one of the factors is continuously variable. Notice that I said one of the factors is continuously variable. This does not leave out the fact that more than one factor. Because I didn't say exactly one. I said one. If you have $5, you have $1. If I said you have exactly $1 and you have $5, then the answer is no. Make sense? I say this because you're getting to the point in math class where words really matter. And they have to have meaning. This is not true for pretty much every other class at every school everywhere. In math class, the words mean something. So integration is multiplication, but one of the factors is continuously variable. That's the sneaky part. That's the calculus, is the study of infinity parts, the continuously variable. Our way of dealing with it here in Calc 3 is the same as the way that we'll deal with it back in Calc 2 and in Calc 1. In Calc 1, we started talking about definite integral. Integration is multiplication, but one of the factors is variable. That just means we have to turn it into addition, where things don't change. So what this means is that integration is addition. Addition is what we use when we don't get to multiply. You wouldn't get to multiply because all the terms are different. If I have 3 plus 4 plus 5, how do I get to use multiplication? I just have to use addition, 3 plus 4 plus 5. But if I've got 4 plus 4 plus 4, all the terms are the same, so we get to use multiplication. That's just 3 times 4. Any questions? An important thing to know when you're learning math, the fact that 3 plus 4 plus 5 is, I don't know, some number, that's not the important part. Quite bugs me in math class when people talk about math. They go, oh, I like math because there's always one answer. That's how I identify people that don't know jack about math. Oh, it's just one answer in math class. You can always count on that. Like, well, how badly do you understand? How badly do you fail to understand math when you think it's about the one answer? It's not about the answer. Here's the reason that we care about right answers in math. First of all, you should care about right answers. But second of all, if I look at all your work and see that the answer is correct, that means your work is probably correct too. Less so back when it's okay to guess things. But in Calc 2, at a certain point, we stopped doing integration by hand. And I just said, have a machine do the definite integral part for you. Because if I'm looking at a correct answer to 5 significant figures, you didn't guess that. You didn't just guess what it was. And so I can kind of go back to the work, your development, your argument for that 5 significant figures and say, they're probably right. And I can go through it kind of quickly. I don't have to look at it very closely. When the 5 significant figures are off, like more than just like the last one, because we don't know how rounding works, which is fine. I know you're like all thinking, I know how that works. I assure you, you really don't. But anyway, if I look at your answer and it's like, oh, there's something wrong with these 5 significant figures, then I can go back and I can look for what happened. What did they plug in incorrectly? Almost always, it was the interval all along. That is almost always the culprit. You went from 0 to 3, and you should have gone from 2 to 5. And then I always know what happens after that. I look at a diagram that has no labels on it whatsoever. Yeah, what? So it's not about the answer. It's about the thinking that goes into the answer. That's what matters. After you get out of calculus and you get your job, your high-paying job as an engineer, where you're thinking you're making so much money, then you realize that you've just been living in the office. What's going on here? And Lockheed is like, oh, well, that's why we call it Lockheed, because we have Lockheed you in the building. And you're working like 170 hours per week. I know there's only 168, but trust me, engineers find a way. And you realize, I have all this money and no way to spend it. And you think back to this moment, it's like, oh man, I should have done something different. But anyway, once you've done all that, I promise you, you're not going to be integrating stuff by hand. You're never going to have to know trigonometric substitution again. It's never going to happen. If you're sitting in your cubicle at some engineering firm and your boss walks over, he's like, oh, hey, what's going on? What you working on? So, well, I'm about to do some trigonometric substitution, just like we taught back in the day. And your boss will be like, oh, wait, you're going to do that by hand? And you'll be like, oh, yeah, wasn't that the point? Your boss is going to be like, oh, I need you to clean out your desk. If you're about to do math by hand as an engineer, you're about to get fired. You know what I mean? It's not about that. It's about understanding what this is about. It's about understanding the thinking that goes behind this stuff. Integration is multiplication, but one of the factors is continuously variable. This is why we should spend less time in math class picking out more examples than we need. When we look at applications of integration, since integration is just multiplication, applications of integration are just applications of multiplication. Places that you're going to use multiplication, those are places that you might have to use integration. Distance is equal to rate times time is our favorite one because engineering. But anytime you have multiplication, area is length times width. Nice multiplication if the length is constant, but if the length is like all continuously variable, it's an integration problem. Work is equal to force times distance. If the force is constant over the distance, yay, we get to use multiplication. If the force is going to be changing over the distance, now it's an integration problem. Then we're like, oh, hang on, can we get away with addition? And the force is like, oh, no, I will be changing continuously. You're like, well, integration problem. Anytime you use multiplication, that's a time that you might be using integration. Sometimes it gets weird. Your gross pay is going to be your hourly wage multiplied by the numbers of hours. If your boss is like, oh, this is the function describing your hourly wage, it's a function of time, get out. That's going to be bad for you. But if that's the case, instead of just saying $30 per hour times the number of hours, you have a variable amount of wages, and it's continuously variable. Not like 30 for the first 8 hours, then 60 for any hour after that. That we can get away with integration, because your wages are variable, but not continuously so. But if they're like, oh, here is a function describing your wages. Now it's an integration problem. You integrate from 0 to 8 hours in the number of hours you work. Questions? Every time you see multiplication, I want you to see integration. Every time you're walking along, I want you to see the derivatives in your, I want to see that, I want you to imagine that vector. Right now, I'm not moving, my direction vector is the 0 vector. When I go here, here's my direction vector. As I slow down, the direction vector gets shorter. So it goes down to 0. And now my direction vector is going this way and increasing. I can't go faster than this. If it's fast zombies in the zombie apocalypse, then I am doomed. All we're doing now is not just walking backwards and forwards, but we're going to go in different directions. And I want you to see this derivative. And the derivative is always pointing where I was going. Now, if I start turning, my derivative starts turning with me, but still, it's tangent to my path. Any questions? I'm not looking at a torque. I'm not worrying about the torque. I'm just worried about my direction. Any questions? For those of you on the YouTubes, I just walked around the desk. That's all. And I pointed in the direction that I was heading. That was my tangent. Now, instead of tangents just being one line, my tangents are going to be vectors. I'm not allowed to fly in front of people in my secret identity, but I assure you it'd be a much better demonstration if instead I could like walk this way, and instead of just changing direction this way, I could change direction this way. Because now I've got 3 different changes: left and right, forwards and backwards, up and down. Whereas your slope now that we have 3 directions that are changing. You know what I mean? So, like I said earlier, Calc 3 is easy to calculate because you know 2/3 of the thing. You know how derivative thinking works. You know how integration thinking works. We just need to take those thoughts and apply them to new objects. I forgot to take roll today. It is a normal thing. Don't panic. I always forget to take roll. Okay, you can go. There is just a natural pause. That's what we call this. Okay, so maybe I'll remember to take roll tomorrow. It's not going to help because everybody's wearing a mask. So how am I supposed to learn names? How am I supposed to put names faces when I only get half a face? I'm already bad at it. Now it's like, oh, you know what Leech needs? More difficulty. And I'm like, oh no, incorrect. I need us to wear hello, my name is labels. For how long? The whole semester, preferably. But anyway, that's just my personal challenge. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.